A subprocedure for single-value players. Two assumptions are relaxed. Players are now multi-minded, and their desired bundles are unknown. Here we define the following specific subprocedure for a set of players X let free of X S to the j plus 1 denote the items not in the unions of Si to the j, where the union is for all index I in X. Definition 12.46. 1 CA proc. Let Mj equals to the argument max of Vi to the j, where the argument of maxima is taken among all index I in N, and the greedy j is empty. For every player I with Vi to the j greater than 0, in descending order of values, perform the following two steps. The first step is shrinking the winning set. The second step is updating the current winners. Shrinking the winning set. If I is not in Wj, allow him to pick a bundle Si to the j plus 1, which is a subset or equals to the free of greedy j s j plus 1 intersect Si to the j such that the size of Si to the j plus 1 is less than equals to the square root of m. In any other case, I in Wj or I does not pick set I to the j plus 1 equals to Si to the j. Updating the current winners. If the size of Si to the j plus 1 is less than equals to the square root of m, add I to any of the allocations W in the set among Wj, Mj, Vdj, for which Si to the j plus 1 is a subset equals to free of W s to the j plus 1. Output s to the j plus 1 and W in the set Wj, Mj, greedy j that maximizes the summations of Vi to the j, summing for all index I in W. Recall that the non-winners then either double their value or retire and reiterate. This is the main conceptual difference from regular direct revelation mechanisms. Here, the players themselves gradually determine their winning set, focusing on one of their desired bundles and their price. Intuitively, it is not clear how a reasonable player should shrink his winning set when approached. Ideally, a player should focus on the desired bundle that intersects few low-value competitors. But in early iterations, this information is not available. Thus, there is no clear cut on how to shrink the winning set, and the resulting mechanism does not contain a dominant strategy. This is exactly the point where we use the new notion of algorithmic implementation. Analysis. We proceed by characterizing the required set D of strategies. We say that player I is loser if silent at iteration j if, when asked to shrink her bundle by 1 CA proc, Vi to the j is greater than equals to Vi bar over 2, retires if losing. I is not in Wj and I is not in Mj, not a winner, and Si to the j intersect the union of Si prime to the j plus 1, where the index for the union I prime is in Wj. So Si to the j intersect such a union is not empty, and Si to the j intersect the unions of Si prime to the j plus 1 for all index set I prime in Mj is also not empty. Remains a loser after pair 2. In other words, a loser if silent loses regardless of the other's actions unless she shrinks her winning set. Let D be all strategies that satisfy in every iteration j. 1. Vi to the j is less than equals to Vi of Si to the j, and if I retires at j, then vi to the j is greater than or equals to vi bar over 2. 2. If I is loser if silent, then she declares a valid desired bundle si to the j plus 1 if such a bundle exists. There clearly exists a polytime algorithm to find a strategy St prime in D that dominates a given strategy St. Hence, D satisfies the second requirement of algorithmic implementation. It remains to show that the approximation is achieved for every combination of strategies from D. Lemma 12.47 1 CA proc is an big O of square root of M local approximation with respect to D. Proof sketch. The pair-2 improvement and the value-bound properties are immediate from the definition of the procedure and the set D. The big O of square root of M algorithmic approximation property follows from the following argument. We need to bound OPT equals to the OPT of the set of the tuple vi to the j and the si bar such that si to the j and the tuple such that I retired at iteration j by the sum of values of the players in wj plus 1. We divide the winners in OPT to 4 sets. Those that are in mj, greedy j, wj, or in none of the above. For the first 3 sets, the 1 CA proc explicitly verifies our need. It remains to handle players in the 4th set. First, notice that such a player is loser if silent. If such a player receives in OPT a bundle with size at least square root of m, we match him to the player with the highest value in mj. There can be at most the square root of m players in OPT with bundles of size at least the square root of m, so we lose a square root of m factor for these players. If a player I in the 4th set receives in OPT a bundle with size at most the square root of m, let si star be that bundle. Since he is a loser if silent, there exists I prime in greedy j such that as I prime to the j intersect si star is not empty and vi to the j is less than or equals to vi prime to the j. We map I to I prime. For any I1, I2 that were mapped to I prime, we have that si1 star intersect si2 star is empty, since both belong to OPT. Since the size of si prime to the j is at most the square root of m, it follows that at most the square root of m players can be mapped to I prime, so we lose a square root of m factor for these players as well. This completes the argument. In the single value case, our bar does not contain all players, so we cannot repeat the argument from the KSM case that immediately linked local approximation and global approximation. However, claim 12.44 still holds, and we use our bar as an intermediate set of virtual players. The link to the true players is as follows. Recall that M denotes the number of items. Definition 12.48. First time shrink. Proc satisfies first time shrink if for any I1, I2 in the set of I such that the size of Si to the j is equal to m and the size of Si to the j plus 1 is less than m, and the Si1 to the j plus 1 intersect Si2 to the j plus 1 is empty. 1 CA proc satisfies thus, since any player that shrinks his winning bundle is added to greedy j.